Okay, in this segment, I want to talk about the different storage classes in C and show some techniques that you might find useful on your homework. In C, there are three different storage classes for variables. Some are implicit based off of where the variable is defined, and in other cases, you can override the default or just specify the type of storage class you want. So the three storage classes are static, and static storage is stored in the data segment, and it persists for the lifetime of the program. Okay, so it doesn't disappear when you return from a subroutine or at any other point. It is allocated at the beginning of the program, and it persists for the lifetime. Now, the scope of the variable depends on where the variable is defined. Okay, but that memory never disappears or is given back to the operating system to give to somebody else. The second type of storage class is called automatic. And automatic variables are in the heap segment of memory and exist just for the lifetime of the function in which they're defined. Okay, so when a function returns all the variables, I'm sorry, I should have said the stack segment. When the function returns, all the variables that are on the stack are basically erased. The stack pointer moves back down, and that memory is free to be used for future stack memory for a future function call. And the third type of storage is dynamic. And dynamic is not indicated by a particular storage modifier keyword in C. It is in the heap segment of memory and requires a C library call, which you've seen, called malloc. Okay, so in the first two cases, static and automatic storage, there are keywords for variables used properly, which indicate that a variable is of that storage class. And for dynamic memory, it requires a function call to the cmalloc function in the runtime library. Okay, so let's just see what this looks like and how you might use it with some examples to make it a little bit less abstract. All right, so if we want a variable to be static, the first thing you'll note is if you define it outside of any function, let's create an integer, and let's call that integer f. Okay, this is static storage by default, persists for lifetime of program. Furthermore, because it's defined outside of any function, also because defined outside of any function is visible, or meaning it's within scope, to all functions in the program unit. Now we'll talk a little bit later about how to make it visible to functions that might be defined in another file, but I don't want to complicate this discussion with that right now. Okay, so F is static storage, and you can say static int F if you want. Okay, that's fine. You just don't have to because it's by default, but if you want to remember or be pedantic about it, you can certainly call it static. All right, so those kind of variables are important. You can think of them as global variables, or you can think of them as sort of file or class scope variables, depending on whether you protect them from other program units or not. And they can be extremely useful. Obviously, if you have a lot of functions in a file and you have too many of them, and a lot of them are writable as well as readable, you can start to lose a sense of what the side effects of the functions are. So you probably have encountered in different programming courses or just in practice that having functions with in-out contracts are easier to track, generally speaking, but there are good uses for variables that are global, at least within a scope. And it's important to know that C supports these and how that relates to the data segment of memory and the concept of static storage. Okay, so I think that's pretty clear. And that this can be an array also. So static int. Now remember, in old C, we needed to know the value. In fact, we have to know this value because there's no way to create a variable before the program executes. So typically this would be so that you didn't have to repeat the value later if you wanted to reuse it. It would be something like this. Okay, so arrays are okay too. Right, and there are limits on how big the data segment is. They're controlled by the operating system, and we'll see the same for the stack. So kind of, if you want to do huge things, I recommend doing it on the heap with malloc, but fairly large things can certainly be supported this way. Now, let's go into a function and define a variable. Well, here we're in main, so let's go into this other function. Now I have a function pair in it, but think of it as just any function for this point, at this point for the purposes of the point I'm making now. And I can declare a variable in here. And as you know, if I just say int f here, this is auto storage, automatic storage by default. You know, we'll say it disappears when function returns, right? You no longer have access to that variable. You can say auto int f by default. Okay, you don't have to put the auto there because it's implied by the fact that it's in a function, but it's important to know the keyword auto means that, and it's implied to modify or to qualify the variable f here. Okay, so we'll just leave auto there for now. And yes, you can do it for arrays, and C99, you can do it for arrays whose size is not known until runtime. We saw all that. But what you might not know is that you can do static int y also. And this forces y to be in data segment, okay? And the value here is that while y is only in scope for pair init, it's not in scope for other functions in either this unit or any other unit, the next time you call the function, it will have the same value that it had the previous time because it's put in persistent memory, okay? And, you know, this might seem, you know, not obviously useful when I just do it in this generic example, but I'll show you a case where, and there are many, but I'll show you a case where it might make your programming a little bit easier. Okay, so let's jump down. Let's talk about the example now, and then we'll jump down to the toString method. So imagine we have a struct, as simple as possible struct, just to illustrate the point, called a pair, and it just has two integers x and y, and we're going to create a constructor for it called pair init, and pair init just initializes a pair. At this point, I'm going to get rid of this because it doesn't do anything. I was just trying to show you the syntax. So pair init just creates a value of a pair. So let's do that. We'll say pair p equals pair init 2, 3. Okay. Now I want to create a toString method, right? And toString method is going to return a string representation as a char star of an instance of the data structure that you're writing the string method for, in this case, a pair. So we'll call that method pair toString. And, you know, presumably it will be used as a pointer to a function to give to some other library that might want to use it to build up a printout of a more complex data structure, say. But in this case, I declare a static array of chars. In this case, I'll just say 10, but obviously you want it to be large enough such that it would accommodate the largest string that this function would ever have to handle, right? And if you don't know what that is really, then of course you could always use malloc, but then you have to deal with the possibility of memory leaks. This just creates one segment in the data region of memory that persists throughout the course of the program. So when I call toString, this is already allocated. And for example, I can use the sprintf function, which is just like printf. It takes a formatting statement, and it, instead of writing to the screen like printf does, it takes the variables that you want to print, the formatting statement for them, and it prints it to memory. In fact, it prints it to, in this case, the static char str. static char array. Okay, so this will basically format it according to the formatting statement and put it in str. Now I can return str to make it in scope to the calling routine. It's the same memory as this, right? And it's not going to go, you're not going to deallocate it. You can't call free on it. But this is just a way of getting it out of this function scope into the calling scope. Okay, and the next time you call the function, it will be executed with str, whatever it was the last time you modified it. And that's fine, because when you get a new pair, you can just write it over it, whatever the next pair values are. All right, so let's just see how this works. I can say printf so I'll just print whatever it returns. And this will be pair to str, and then I'll just pass an instance of a pair. All right, so let's see if that works. I'm sure I have some errors. Yeah, I've got a million errors. Let me just fix those really quickly. Okay, so I turned my notional code into real code. I had a bunch of little errors, so I'll just summarize quickly what I did. Pair init is going to create a pair by reference, so I just pass in a pointer to a pair, and the effective pair init is just to set the fields of the pair. I could also have it return the pointer. I just made it return void for simplicity for this example. A lot of constructors will say this returns a pair star, and it will set it and return it. Either way is fine, but I'll keep that as void. And so now the pair init works. I just give it the pointer to the pair. I had to initialize the pair. I forgot to do that. And then the toString method takes a pointer to the pair. And I also had to set the function prototypes. Okay, but otherwise it was basically correct. So now that that works, hopefully this will just print out the pair for me. And let's just create another pair. Sorry. Let's do this. And we'll just verify that we can use static memory to change the value of what we're printing. So the first pair is 2, 3. The second one says 3, 1. Okay, so if everything works well, it'll print out 2 pairs. And we won't need to allocate or deallocate any memory, and we won't need to use malloc at all. So we'll just run it as a.out, plump, and printed the 2 pairs. Okay, so of course, I didn't mention explicitly because this is something that we've encountered already, but the third type of memory, dynamic memory, just uses malloc, right? And when we use malloc, we request memory from the operating system. We talked a little about virtual addresses and paging, but from the programmer's perspective, you're just requesting a buffer of memory, and it's the operating system's job to give it to you. And if it can't, it has to tell you that it can't give it to you. And when you're finished with that memory, if you free it, it will make sure when you don't need it anymore, it will ensure that you have as large a pool possible of memory to draw from in the future when you might need memory again. And if you're not careful and you don't free and you keep mallocing, then you have a memory leak, which will become catastrophic and likely eventually run out of system memory and crash your program. Okay, so those are the basic ideas, and they should help make it easier to organize certain aspects of your program.